Well, brilliant, Viv. Once again, thank you very, very much indeed for that. But aren't you giving a little bit too much away here about how nuclei work for the time being? Anyway.
Yes, I've given a little bit away, but you wait to the next presentation, you'll find out an awful lot more about nuclei then, but that'll wait a little while while I do a few other things. Give somebody else a chance to present something.
Well, I'm looking forward to seeing how you fuse these things, how you start creating matter. That's going to be fun. That's going to be about a month or so's time, because we're going to switch to some other things in the first instance. Anyway, can I throw everything open for questions for Viv?
I don't know where to start. I have a lot of thoughts which are going through my mind as I was listening to this talk. As you know, that I've spent nearly 25, 30 years of my life doing the nuclear physics, nuclear structure. We left the ground states a long time ago behind us. That was a long, long time ago, except for the people who work in the super heavy elements and then far away from the drip line, who wants to get the activities going on that one. By the way, I should also say that those people who are working there also use the alpha cluster models these days. And I was surprised because alpha cluster model was a very old model, which was formulated back in 1940s or some such kind of a time. And then there are several kinds of that, like you talked about the triangular structures, and there have been several things which have been tried around. And you also mentioned about the lead-208 is the heaviest element that you could ever find as a stable one. Until recently, about 20 years ago or so, lead-209 or bismuth-209 was considered to be also very stable. And finally, they found its half-life to be 10 to the power of 19 years or something like that, which is like more than 1 million times the age of the universe. So given that, I would not be surprised if someday people will say, yeah, lead-208 is after all is not stable. It may be only 10 to the power of 20 years or some such kind of a thing, So one can come up with that kind of a argument also. We don't know that. Because like I said, until about 10, 20 years ago, bismuth-209, which is 100% abundance of the bismuth, 83 is the atomic number, and it was considered stable. But now we say, yeah, it's 10 to the power of 19 million times the age of the universe. I have one question though. Which, of course, you made your rules. I see that you might have made up your rules. Something very similar to what this alpha cluster people are making their rules in the good old days. My question is, when you take the layers of structures which are putting in here, does this have any correspondence with respect to what is the available energy at the energy state that they occupy? I mean, can you say the outer layers are higher energy compared to lower states, or there is no correspondence at all?
This I didn't investigate. My impression is that the lower atomic number layers on the upper ends of the structures probably have slightly less binding energy. Or
take the same atomic nucleus, and you've got different layers you're building up to make up the final number of atomic numbers Z and N which you're creating. So can we say that the outer layers are higher energy states, open to be easily knocked out, and then whereas the deeper ones are the ones which are more strongly bound, and hence stay.
I won't offer or attempt to offer an explanation about that. It's something that I haven't explored. I believe that the binding energy in all of them will not be the same. I think it will be different, but I haven't gone that far in this presentation. I think it's more, as I said, it's more important to just get the basics across and leave it to other people who have an interest. It'd be better to do that because there's still an enormous number of topics I have to cover to get through the whole universe. And as far as
the other question I have is if I look at your carbon nucleus, we had 2 layers with 3 protons and 3 neutrons in each layer. In fact, yeah. That's not an alpha particle model.
Well, I've seen an alpha particle model where they have 3 alpha particles clustered in that equilateral triangular shape. The only problem, in order to do that, the alpha particles have to be exceedingly small. Now, the individual nucleons have to be exceedingly small. And that just doesn't match the observed size of protons or neutrons. So, like I said, there have been many, many different models tried. Some make some agreement with experiment over short ranges, and certainly, yes, three alpha particles in an equilateral triangle is one of them that matches the observed structure of a carbon nucleus, but it doesn't. You can't use that anywhere else, and just the size of the nucleons would not prevent that. Would prevent that from that type of structure from occurring.
I was more concerned about your layer. In each layer, there are 6 particles, and each one has got 3 protons and 3 neutrons. That's what your picture has. And when I looked at it, I said, this is not an alpha particle, because the one which each layer contains like more like 2 lithium-6 coupled to 1 carbon-12. And that's what bothered me.
The carbon-12, none of the nucleons are in an alpha particle structure. And you'll see that if you go back to the slide that I showed about the nuclear densities as they're measured by Hofmeister and his group, you'll see the nuclear density drops down in the middle. And like I said at the beginning, there are a number of models which can match properties of nuclei over a short range. And saying that one of them, yes, it does that, which is what you're saying, the 3 alpha particle models can do with the carbon-12 nucleus, but it doesn't extend to anywhere else. That's the whole.
Sorry, I think if I'm looking at Viv's model, his model of carbon isn't a set of alpha particles; it's a set of alpha particle configuration.
It is not, yeah.
Yes,
it is not. It is not there. Yeah.
You have this 3 and 4 configuration thing. Yeah. The thing really it's sort of like on the outside 3 half alpha particles, on the inside 3 half shared alpha particles in a group of 3. So it's a difference between configuration and the actual thing being an alpha particle, which is like the old model.
Yeah, absolutely.
Yeah. So.
What I'm saying is basically, the main concern is the following: when you're dealing with the ground states and then you're dealing with this one, but the thing is there are enormous amount of information which has been collected for several excitations, several transitions, several reactions. It is like it was like an industry which has gone for about more than half a century around the world, and there are various phenomena of the nuclear things which we see. And then try to understand in terms of what you can call the shell model, collective models, modified shell models, where you put in configuration mixings and etc., clustering, so many things. And then we talk about halo nucleus. You talk about the skin. That's called the halo nucleus, neutron skin, proton, mostly neutron skin. They talk about all these things. So what I'm thinking about is that given that amount, if you look at the semi-qualitative understanding of this, semi-quantitative understanding of the structures, I think Shalmore has done a great job. In fact, it is surprising, it's shocking, in fact, why he does such a good job. Because I can tell you offhand, I can tell you what the spin of a ground state of a nucleus is for any odd nucleus, approximately for most of them. In fact, there are only few exceptions where the single particle model fails. It's very few cases, in fact. It also gets pretty close to what you would get as nuclear magnetic moments. It also gets pretty close to what you could get as the electric quadrupole moments, except when you go to very collective nuclei in between the shells, in fact. And these are involved in excitations. These are involved in the transfer reactions. These are really many things. When you talk about the neutron-rich nuclei, these are not prepared stable-wise, in fact. These are prepared from evaporations. You take 2 heavy nuclei and blast them, and then you create a very messy system.
Excuse me.
So you make a messy system, and there are the neutrons being evaporated, coming down into the different things. So it is not that they're slowly we are not really slowly cooking into heavier nuclei with a more number of neutrons. It doesn't happen.
You have to excuse me a little, Shari. You talk exceedingly fast.
I can't help it. My students complain all the time. All the time.
You were more passing comment than asking a question, were you not?
No, what I'm saying, there's so much, yeah, there's so much of data which is available, and I'm trying to think, making this kind of a model. I cannot see ourselves explaining any of those enormous amount of phenomena which has been measured and documented in the literature. In fact, that's what I'm saying. Structural executions.
I know. I've seen quite a few papers where people have gone through and calculated many properties. From what I have seen, most of them is from theoretical considerations of quarks and gluons. Unfortunately, they have the requirement in order to match the mass of the nucleons or the nuclei. They really need to have the quarks going around at almost the speed of light. Theoretical nuclear physics has been around for a long time, and yes, they have been able to get some good matches in some area, but the object is not to get a good match in one area and ignore other aspects of it. The object is to get a good match across all of them, and that's all I'm suggesting this model does. And it would be I think it would be a good idea to give it a go yourself to see how it makes out. And as I said, getting a model, getting 3 or 4 separate models that together can give you a reasonable explanation across a range of nuclei is not the same as getting one model that can fit everything in together, which is what I believe mine does.
Yeah, can I comment? I'm especially impressed by the way this works down at the low Z nuclei as well, which you presented in your last in your last talk. But can I ask, is that where you've got your numbers of 0.8 MeV per nucleon and so forth from looking at the mass deficit of those low number isotopes, or is that just...
No, it literally. I like the semi-quantitative approach. It literally comes from an average. You study it for a while, you draw up a few, you try a few examples, and then you have to get something that is constant. I mean, there is no way that there is only a 0.8 MeV binding energy per nucleon in the magnetic layers for each and every one of them. There's just no way that can be the case. And all I have done is gone through and selected an average. I mean, this whole model needs an enormous amount more work done on it to get a closer match. And I'm just going to leave that to others rather than... Okay. You know, I could keep going on that for a long time, but then, like I said, there's still an enormous amount of work to go. Got to go through electrons around atoms, got to go through gravity and all that sort of thing. Yeah. So
it's a very ambitious project. Yeah, it's a very ambitious project. I commend you.
Yeah, I am going to get there all the way.
I think what's spectacularly different about this model is that it's looking inside the element, inside protons and neutrons in terms of their inner charge distribution, and taking that as the strong nuclear binding. This is quite a departure from thinking about quark-gluon models, which, as Viv says, and also as I pointed out in one of the earlier talks, have problems in terms of just the energies that the quarks have to have in such systems, and very near light speed. A lot of these things are almost photons in terms of their mass energy, because they have to be so fast. So there's almost no rest mass in these quarks at all. And
John, there are two kinds of quarks. One is called John. There are two kinds of quarks. So, current quarks and constituent quarks. You know these things, right? The constituent quarks are the ones which have got the mass about the 1/3 of the mass of the nucleon approximately, so that they don't have to go that fast. And the current quarks are the ones which have got the small masses. They go at the relativistic speeds, in fact. And then who tells them where to be? Well, God knows, not me. So,
yeah, but if you look inside a nucleon, if you look inside a proton or a neutron, you don't really find quarks with 1/3 of the mass of the proton.
Of course not.
In fact, I think the biggest ones, yeah, you do it very occasionally, but if you look at the structure functions, they're way down. So they're all these things. Yeah.
The other thing about the quark and gluon model is that they have never been separately isolated and detected, and neither has the concept of fractional charge. And at least in this model, as John points out and I point out, we have a reason for the origin of the whole charge, that being the angular momentum of the object. And there is no way under this model that you can get fractional charge, although I will admit you can get a whole charge for a fractional time, which could have some of the properties of fractional charge. But so far, there has been no detection of any fractional charge. There's been no detection of quarks. There's been no detection of gluons. And indeed, to make the models work, they've had to introduce the concept that the greater the separation distance between quarks and between quarks, and the stronger is the gluon interaction, which would tend to suggest that those satellite nuclei that form around, quite unstable, should be the most stable nuclei at all, if quark-gluon binding is what's holding nucleons together. It just doesn't work that way. And so this is why I say...
I'll address this next week. I'll talk about this a bit on the quark models when I give my talk next week. So we call this one as the non-physical models, in fact. There's the physical models, non-physical models. There's no physics, and non-physics.
I'm a big fan of physical models, and then using mathematics to support the physical. And I have, sorry, Jerry, I have really no interest. Yeah, and I've used this all the way through, and including the stuff that I'm doing on gravity and expanding on general relativity and that sort of thing. The whole thing is work out the physics first and then use mathematics. And I've read so many papers where people saying they're describing what a topic that I'm interested in. Then you go through, it's entirely mathematical with no diagrams, and you think, no. Physics, I think some mathematicians have hijacked physics as if unless you have a mathematical explanation, no matter how complex it is, no matter how difficult it is for mere mortals like us to follow, somebody else can't follow it and therefore says, oh, it must be right because it gets this answer. I won't go along with that.
I've got another question though. You talked about iron being the stablest, which it is, the highest binding energy per nucleon isotope is iron. Does your model say why that's the case? If you add up all those nuclear binding energies, does that give you a minimum number?
It does. I mean, basically, the alpha particle is the model with the highest binding between a proton and a neutron. And then the iron 56, it's not an exact calculation what I found. It's a case of, look, I found out that if you put 0.8 MeV per c² for each nucleon between the layers, you can then go through and work out from the approximate diameter of the Fe56, you can work out then that requires the still quite strong binding between the nucleons within the layer. But no, I haven't used that model to work out specific things like that. That's left for nuclear. All the younger up-and-coming nuclear physicists can do that much easier than I can. Besides, if I was doing that, I couldn't make this progress in gravity.
Yeah, that's true.
But to follow up on John's question, if I decode the iron to be the most stable and the highest binding energy, and if I think about alpha particle model, I would have thought iron 52 will be the most strongest bound particle. In fact, it's not even stable.
Yeah, but you're thinking in terms of separate alphas again.
Yeah, I think about alpha particle model, alpha clusters. Then I would have thought iron 52 would be the candidate. Even if I give the iron to be the preferred nucleus, I would have thought iron 52 would be the most strongly bound, most abundant isotope, but it's not stable.
You're thinking about it being a set of separate alpha particles, which are then bound.
Exactly. Yeah.
No, but
that's right.
That's quite different. These are all overlapping.
That's different from his model,
Yeah.
Again, there are a whole lot of other models, but again, if you're using sort of separate particles, separate alpha particle combinations, you do run, and once you get past calcium, for example, you run into the fact that the most stable isotopes then have more neutrons than alpha particles, which have got to be put somewhere. And these are all of these things that this is, like I said, it's very easy to get a theory that will cover some aspects of nuclear physics. And all I'm trying to suggest is that this one model will cover them all. And I'd be very interested in somebody came. I mean, I think the best you'll find, well, as I've found myself, like I've picked on certain structures, certain layers, but there are other layers that can, other structures with different layers. Like I said, with the first example, the aluminium, you can get, and also with calcium, you can get one with 5 layers and one with 4 layers. And by the time you get to palladium and higher, or even other nuclei, you go through, you look at the table of isotopes, and then you'll suddenly find one isotope has got 2 decay modes. Now, I don't know how other models account for that, but this model accounts for it simply that whatever structure that I have put down is not the only one. It's just one that gives a reasonably close match. I mean, some of mine, the ones I picked out, my half-lives between what I predict and what is observed is up to a minute or so. Which but at the same time, I've shown in the aluminium structure that the same isotope with different structures could have half-life differences of factors order of 100 or more, that sort of thing. So all of this has got to go. You can go through it with this model. I'm not saying that I've done it. I've just done it for a dozen elements and a bit over.
I think what you've done, Viv, is you've set a ship out there sailing with an idea of a completely different kind of model. And I think you're absolutely right. I mean, you could now spend your entire life calculating 9,000 different combinations. Don't do that. You're not allowed. That's fine. The model's out there. Let other people have a look at it. It's one of many. And now it's up to natural selection to see which one will sort of make a difference here. And the great thing about this is a complete departure. And I love it for that. And I'm very, very curious to see how it develops from here on in.
Me too.
That's good. Yeah, that's excellent. Yeah, like I said, that's a lot of this one. It's a lot of work. I can see that.
I have another question. I have another. You're talking about this division by zero binding, where you get this cancellation as the protons, and I love that, and also this minimum that you have, and that's a very strong binding, interlayer binding, and that the binding is relatively weak between layers. But wouldn't you then expect that fission to be something that happens interlayer rather than intralayer? If it was weaker between layers, make some comment on that, or
Well,
I think that's
one
a
thing.
good question, by the way. But nonetheless, how have you been thinking about that?
Well, first of all, my thoughts on strong nuclear binding. Yes, you had two oscillations overlapping each other at very short distances, and electrically would give, as I said, that division by zero binding. With the passage of time, I became aware that no, there is a strong magnetic field contribution to that as well. That magnetic field contribution also has a very limited range, because that's basically a 1 over r cubed and not 1 over r squared, which means it also drops down very, very rapidly. And I would not be surprised if the magnetic binding was almost as strong as the what I call that division by zero binding. I just haven't done those calculations, but I will.
I think you're right about that. I think what you're saying is that there's a magnetic flux through a system which is coupled from layer to layer, and that can be a very, very strong force, I think, at the kind of distances we're talking about.
Yes, the reason why I say it's relatively weak, I may actually be wrong on this. The reason I say it's relatively weak, because so much of the very strong magnetic field is going in to form the binding within layers.
I think you're right about that, and I think that what you might see a magnetic flux going through all the layers, like a thread coming through the whole thing and binding it on the outside.
No, you won't get that. The reason for that is, if you did that, then there would be a strong, the whole nucleus would have a magnetic moment. But whereas all of the even A, even Z nuclei, I think almost all of them, I think one of them has about a 0.1 UB. The rest of them have 0. And that's the strongest possible indication that there's very little continuing between the layers.
Okay.
If I could just extend on John's question, where this question really struck me is when you look at if you have two like Li6s on top of each other, you can see that the magnetic fields will be exactly lined up one on top of the other. But what if you have different size? If you have an alpha particle on top of an Li6, then vertically, each nucleon the magnetic fields are not on top of each other. Some of them are in between. So wouldn't that cause a weaker binding between the layers than when they are exactly symmetrical above one another?
Mm-hmm.
Intuitively, yes. I mean, but that's something that needs to be investigated.
When I was,
it might be a bit too advanced for your chemistry students, though.
The way I looked at this when I was looking at Viv's things is that they weren't precisely centrally aligned, but that they could switch a little bit left or right, so that they did align, did line up.
Yes, that's something that you have to work out. And the one thing I did notice, the carbon-6 nucleus is two lithium. Sorry, the carbon-12 nucleus is two lithium-6 triangles on top of each other.
Yep, that's what you did. Yeah. Mm-hmm.
And you got the protons on the outside aligned on top of each other. They give very strong magnetic binding, which is actually pulling the carbon-6 nuclei, the nucleons in the carbon-6 in quite considerably. And that, I believe, is one example where what you were saying, John, about the magnetic moments lining up. And that's one of the reasons why the binding energy for carbon-6, binding energy per nucleon for carbon-6 is nearly 30% stronger than it is in lithium, sorry, carbon-12 than in lithium-6. Even though it's just two structures stopped on, and that's one situation where the magnetic field is really dominating.
I'm just thinking that thinking about this, I'll need to think more about it, and it'd be fun sitting down with some balls and sticking these things together at some stage. But one thing that could be, and I take on board your point about the zero moment of the even A, even Z systems. Experiment always trumps everything else. But what you could imagine is it like stitching. Absolutely, no argument. End of argument. Lovely, I love it. But you could imagine something going like stitching, sort of coming up through a layer and then going through the next one, and coming up through the next one. Couldn't you?
Yeah.
Yes, it has to be that way. I mean, because you've got nucleons with a positive magnetic moment. Protons with a positive magnetic moment, neutrons with a negative magnetic moment. They're next to each other. It would make a wonderful exercise for if somebody want to do a theoretical physics, nuclear physics PhD, just to go through and find out all those different combinations that could occur. Yeah.
Your career has missed one thing, and I've always thought it would be very good for you. Half a dozen PhD students.
I know.
That'd learn you.
Oh, I remember when I was one, and I learned myself a lot then.
I'm sure you gave your supervisor a couple of grey hairs here and there.
John, just regarding my supervisor, his first name was also John, and his hair was as white as yours. And he taught me a lot too, same as you have.
Thank you. Good. Well, I think there's a lot of mileage in this model, and as you say, perhaps it's the work for many excellent folk for many years, really, to extend the Robinson model here and think about it together. Yeah. So thank you very much indeed for that. Again, I'm all run out of questions now on this. Anyone else got any more?
I just want to comment on your question, John, about interlayer versus intralayer fission, in fact. And I was thinking after listening to this, possibly the mass fragmentation, which you'll find that what's called Magnanus arc, we call them, in fact, in my students call that one. So that the fact that you don't have two binary fission exactly of fixed masses, and it distributes over anywhere from 160 all the way down to 70 tells us that there must be some intra-layer fission also. That's what I would think. Because of the fact that the mass fragmentation is not unique and is distributed over several masses, tells me that the upper layers and lower layers are somehow getting mixed up once in a while. And then they cause you various fragmentations, in fact, yeah.
That's a very nice thing about this model as well. That explains that in the simplest way I've seen. I don't know if you...
Exactly. That's what you can say. You can imagine that.
Yeah. Good.
Because the top is only 6%. You know, if you look at the curve which we have there, we worked on that one for a different reason, not for the physics, but for the applications. In fact, the top where you got mass number about 199, molybdenum 99, molybdenum 100. That's only 6% of the probability. So the rest of it is all distributed all over the place. Several masses are coming. So it is not a unique fragmentation. It is distributed over several masses, which corresponds to the possibility that there's an intra-layer of fission taking place.
I remember being confused by this not confused by, but intrigued by it, the fact that it didn't split evenly. And I've always been wondering why until recently. Thank you, Viv.
I think you'll find that this will explain a lot more. So, Chari, do you have access to PhD students?
Oh, I stopped doing that.
Okay.
But the thing is, right now I'm 70 plus right now, and that's enough for me to do all the PhD students.
Oh, a young man! You're a young man, Chari.
Oh, I'm a young man, 70. Yeah, that's right. Youngest in this. Oh, forget. There is Arnie. The rest
of okay.
Shall we stop recording for a little while and perhaps go over to a meeting?
Sure. Thanks very much, Viv. That was wonderful.
That was great.
Thank you.